Hey guys, what's up? Eddie Alho here with KissAnalog.com. Today what I want to do is I want to look at a Class D amplifier. I want to kind of explain how the output works, or how Class D works. So we're going to look at the output, where it all happens, okay? And we have this board. It's an eval card from Efficient Power Conversion. You may have seen it before in other videos. I have a playlist, and I'll put the link below, where I've checked. I've done several videos where I've checked performance on this. Today I want to show you what's going on inside, okay? And so what we're going to do is we're going to look at the output circuit to start with, okay? And I'm going to kind of explain how that works. So after that short explanation, then we're going to come over and look at the board, give you a nice close-up of the board and how the setup is done. And then we're going to look at some screenshots, and hopefully that'll help you see how these Class Ds work, give you a better idea. Okay? Alright, let's do it. Alright, I've got my board. And sorry about the drawing in advance, but let me go over the circuit real fast. The output of a Class D amplifier might look a lot like the output of a Class AB amp. Push-pull circuitry. You got, I'm using switches for my transistors. So you might have a switch up here that's pulling the voltage towards plus, and then that turns off, and this one turns on and pulls it towards minus. So one pulls it up here and one pulls it down here. And yes, it's a square wave. That's the difference between a Class D and a Class AB. Class AB, these would be, the transistors would be working as amplifiers. They'd be amplifying the signal that they see. Where in this case, we don't want to dissipate power across these transistors, so we just turn them on, turn them off, turn them on, turn them off. And if you do that and you modulate the pulse width, then you can, the overall RMS voltage out here, you can change to be what you want. And for instance, if you start off 50% duty cycle, you're at the plus voltage, the same amount of time you're at the minus voltage. So the voltage, your RMS voltage out here is going to be 0. But then when you start going, this guy starts to stay on more often than this guy is. So the frequency, let's say 400 kilohertz, the frequency is going to be the same. So you have the same period of time for a full cycle. But if this guy is on for a higher proportion of that cycle than this guy, then the duty cycle might go to, say, 80%. And vice versa, if this guy's on for more of the time than this guy is on, then maybe the duty cycle is only 20%. So the voltage out here will climb up near, plus V. There's some voltage drops and stuff, so it can't get all the way there. But it'll climb up near plus V, and then it'll drop down near minus V when this guy is conducting more of the time. So it's really like the average time that it's sitting at these duty cycles, and it won't get all the way down to minus in just a few cycles like I showed. I mean, we could be operating at 400 kilohertz, and even if we're producing a 20 kilohertz waveform, or even say even the bandwidth is 100K, this guy would be operating at least 4 times faster than the frequency that we might see on the output. What we're going to do today is we're going to look at the output, and I'm going to put a 1 kilohertz sine wave in, and we're going to see a 1 kilohertz sine wave out with some amplification. Well, I'm also going to look at this switching node, because that's where the magic's kind of happening. Well, maybe the magic's in the filter. Guess it depends on where you are, right? But right here, the switching node, we'll see how it's doing it, and we'll look at, we'll look at the, on a sine wave, where it crosses 0, it's going to do that twice, right? As it comes plus, then as it goes minus. As it crosses 0, we'll look at that point, because that's the midway point. That's when we should be 50% duty cycle. And then when the sine wave's near the top, we should be at the max duty cycle. And, of course, when it's down towards the bottom of the sine wave, we'll see the minimum duty cycle. So let's take a look at that on the scope. And I'm going to show you the setup too, okay? So let's do that. Alright, so as far as the setup goes, I'm going to be using this GW Instack power supply. It's a dual tracking output, so it has 2 outputs, and These kind of power supplies, if you haven't used one before, you can use each output independently to do its own thing, or you can push these buttons and put them in parallel, and you can get your whole output off just one side. It's called the master, and this kind, the other side's called the slave. Or you can put them in series, so it's like putting two batteries in series, and that's what we're going to do. So we'll have a plus here. The middle point of the the center of the two batteries, the center point is our ground reference, and so that'll be this yellow guy. And internally to the power supply, these two terminals, the plus of this guy and the minus of this guy, are tied together. So we only have to, we could tap in there or tap in this side, doesn't matter. Okay, and then this is going to be our negative voltage. So we'll come down to the board just like that. Okay, plus minus with our reference point in the middle. Okay, I'm going to come over and show you the board, and I'll show you all this close-ups of all this stuff, and we'll take a look. Now, by the way, this voltage control and this current control are the only things I have to worry about. So what I'll do is I'll put one of these meters in volts and one in current, because if there's a fault, it doesn't matter if it's on plus side or minus side most of the time, I'm going to see the current just jump up. And as far as voltage, whatever voltage I see on this battery or this output, I'm going to see the same thing. It'll be the same thing on this side. So that way it makes it convenient. I can look at voltage and current at the same time, and it's just kind of a nice thing as I bring up the voltage slow. This power supply wants to see it plus minus 20 before I get the LEDs on the board saying good. Otherwise I get a couple red LEDs until I get to 20 volts. So I'm going to go to about 24 volts. Now I could just set a power supply to say 24 volts like this, hit the on button. Some people call that the smoke test. I don't know why they want to test the smoke. I don't like to. So I like to bring it up slow and make sure the current's not doing something erratic. And then I could shut down right away before I do the smoke test and let the smoke out. I like to keep the smoke inside. Let those, secret smoke places stay where they are. I don't want to see it. So anyway, that's just a tip on powering up, especially the first time you reconnect your stuff. You may have tested this board a million times and you've got a lot of confidence and you, like, I know it works, I'm just going to flip the power on. But if you just set up your leads, even though you've done it a bunch of times, you could have made a mistake. You're thinking about lunch. But you know what I'm saying. So the very first time you set up, just to check your setup, bring the voltage up slow. Good tip. Saves you parts. Saves from having to wear the glasses. Well, which I should anyway, right? I usually put a plastic protector on, honestly, because I like to play it safe. But yeah, playing it safe. It's worked out well for me. So just that tip in there. Okay, I'm going to bring the camera over. We're going to take a look at this. And I'm going to use this resistor. It's one of these non-inductive resistors, 8 ohm resistor. We're not going to draw a lot of power because we're just going to look at the signals and see how that square wave, puts out that sine wave. So we're going to just take a look at that. I'm going to do some other videos looking at the signal from the input to this output so you can kind of see how that processing works. Okay, if you're interested in that, give me a thumbs up and let me know. Appreciate the thumbs up, by the way. That really helps the videos. There's a volume control that turns on both sides, so that's right here. I'll be using that. And so it does have the preamplifier stage built into here. This is a nice board, and I need to send it back to EPC. Kind of kept it longer than I should probably, but I'm going to do this video, maybe one more if you guys really want to see that other stuff, okay? And then I got to send it back. So, alright guys, hope you like this video. Hope it's going to teach you something. I think it's really interesting. I think this Class D stuff is pretty cool. So, alright guys, let's come over here and take a closer look. Alright, so I kind of wanted to show you the setup. We're going to use a differential probe right here. And that's because we don't want to ground one of these two terminals. Okay, so we're going to use a differential probe here. If you didn't have a differential probe, you just use 2 channels and you tie the grounds together and you put the probes here and you do the subtraction thing. And the other scope we're going to just put here, and that one we will tie to ground, which, you know, this circuit here, we have the plus minus voltage. The center of them is going to be basically referenced to ground, so it'll be tied to that ground. So we just don't want to tie one of these to that ground, okay? Just a little safety note on grounds. So I have a differential probe, so I'll put it here. All right, just wanted to cover that. Okay, so let's just go over this setup. Here's our board, of course, and here's our 3 leads coming from the power supply. So we have our plus, the red, and the one in the middle is the reference point, the ground, and the blue one is our negative voltage, okay? And then this is our output. It's a 2-channel output, but we're going to be just looking at this one channel. This is the THD meters, and over here are the differential probes that go to this differential Pintec DP25. And I'm going to be probing right down here with this scope probe right down on the switch. You know, there's 2 diodes. I'll zoom in so you can see that. But we'll be probing there. So this is one channel, the top channel we're going to be looking at. The signals coming right here. This red and black signal is coming into this RCA jack. It also has, just for reference, XLR input. Both sides do. And here's the volume control, the gain from the preamp stage to the power amp stage, which is right through here with these inductors, okay? And my other videos, I kind of go more into this, but I'll show you a quick close-up of this. Okay, and there is this is the output section of the channel we're looking at. This is the output inductor, and there's a C over here. You can see these little white polycaps. There's one here and there's one over there, but right there, you see these 2 tiny little guys right there. Look how small they are. They're our FETs, our GaN FETs. Now this amplifier is capable of 150 watts output, which it does that without even needing a heat sink. See the 2 other FETs right here? So we have 2 of them here and 2 of them here. That's our bridge. So I drew a picture showing just 2 of them, these 2 up here, and then we have the 2 down here. And right here on these diodes is where I'm going to be probing. That's that switching node. I didn't draw the diodes in there, but essentially they're in parallel with the FETs. And one side goes to this side of the inductor, and this guy goes to this side of the inductor, okay? And you can kind of see the size of things relative to this probe. Here's the drive section for this, drive section for this, and here's some of the circuitry that is telling how to do that. So if you want to see me probe that, let me know in the comments, okay? And our output, or our big old capacitors for the power supply around the edge here. And that's what the scope tip will look like as I'm holding it down, just to give you a size reference of how small these parts are. Alright, there's the power supply, and you can see the switch network there that you can configure for independent, series, or parallel mode. And the knobs on the right are for the master, which is the red and yellow output. And by the way, this yellow, these 2 guys are internally connected together. So it's like having 2 batteries on top of each other. Plus, minus, plus, minus. So this is our negative voltage, our VCC. Negative VCC is the blue, and plus VCC is red. And as I bring up the input voltage, like right there, 4 volts, very little current. And if I switch this over, you'll see the same voltage on this side. So that's our minus voltage, our plus voltage. And if I put them both over here, I see current. So I just put one on volts and one on current. Alright guys, the Signet generator is the guy on top, and it's all set up 1 kilohertz. It's actually putting out 230 millivolts peak to peak, and the preamp will take care of the rest of it for us. The meter on the bottom is our Keithley, our THD meter, and it's set at THD, and right now it says it's overflow because it doesn't see anything. Really nice meter, by the way. Okay, I'll go through my setup real fast on the scope on this really cool GW Instec scope. It's the MDO mixed mode, mixed domain scope, so I have a scope with the spectrum built in. Channel 1, we're going to be looking at that drive signal, okay? The switching node. And channel 2 is the differential probe. That's going to be looking at the output. Because the output's not referenced to ground, channel 1 will be. So we want to float this side, so we're going to use a differential probe to take that reading. So it's set for times 20. You can see that. And I'm also going to just bandwidth limit it 20 meg and DC couple. And that's just to filter out some high frequency noise. So because my setup and the readings, I don't want to get caught up into trying to clean that up. So that's why. And channel 1 will be 10x for the scope probe, normal 10x, same thing, 20 megahertz bandwidth limited. Okay, so I turn off my menus, get my screen back. Love that about the GW InSec. Right now my horizontal bandwidth is set for 1 millisecond, and channel 1 set for 20 millivolts per division, channel 2 set for 4 volts. They're both DC coupled. I've also got some measurements selected. So I've got duty cycle for channel 1, peak to peak for channel 1, and RMS for channel 1. And channel 2, same thing, duty cycle, peak to peak, and RMS. I could do 2 more measurements if I wanted with this scope, but I think that's enough for now. Alright, so what we're going to do is I'm probing, and I'm going to probe that node and then bring up the power. Okay, here we go. And I'm at 20, I'm going to go to 24 volts. So the yellow waveform, you can see that's that drive signal, okay? I'll zoom in, sorry for reaching. So there's that signal, not being triggered on it right now, but kind of a square wave. Okay, and then I'm going to zoom out so we can look at the 1 kilohertz sine wave down here. Okay, now let me bring up that signal, the amplifier. Okay, now here I'll say and bring it up like this. We're going to bring it up. I'll kind of bring it up to there high. Alright, so let's freeze that. Okay, now I'm going to turn off the power so we can zoom in on that. And I don't have to worry about slipping the probe or something. Okay, I zoomed out so you could just see what I'm doing. What I'm going to do, first I'm going to zoom the main time band, just so we have a cycle or two to look at, just to make everything else simpler. Okay, we got a couple cycles there, right? Now I'm going to hit the zoom button, and we're going to zoom right in on that. And let me see, I'm just curious, I didn't even check. Okay, my record length is set for max, that's good. Deep memory, awesome. Get good resolution even after you grab that much information. Alright guys, you know what? I think a few people bought this scope since watching me do this. It's time for GW to help me out, right? Alright, well, maybe someday. Okay. Now, what I'm doing is, see these green brackets up here? And this is our original window. When I turn off the zoom, that's what we're seeing right here. And then when I put the zoom in, we're just seeing this part. Okay. What I'm going to do is I'm going to center in the screen. See right there, that's the trigger mark. I'm going to put the waveform, and right now we're right about the minus point. But see right here, this is our reference point. So right there is our ground. So I want to get one of these 2 points where it crosses ground right here in the middle. And I'll explain why. What I'm going to do is when its output is essentially 0 volts, remember, our duty cycle should be about 50%, right? So now what we want to do is zoom in right here, and that's this green window. So let's make that smaller. See? And that's our 0 point. We're zooming in right there. Okay, look at that duty cycle. Doesn't that look like about 50%? Let's get the cursors. Now, when I hit the cursors, you notice you see the cursors right here, so I can slide it over here where it's in that green window, and then I can see it starting to appear. Okay, and I got them both locked together. That's pretty awesome. I didn't mean to do that. That was just dumb luck. Okay, I'm going to switch over to the first one, and you see that little line going up and down? I want to get the bottom of it just for fun. And then I'm going to move the other one to the same place on the next cycle. See, it's down the bottom, but instead I'm going to put it at the top. This would do two things. One thing, the difference in voltage would be shown right here from that little hash mark and this hash mark. The other thing is there's a time delay, the rise time, and we'll kind of take that into account as far as this duty cycle. Okay, I'm zooming in on the screen again so you can see this. Now, I'm going to change from duty cycle, I'm going to change to seconds. And if you look up here at the window, and if I go right here, that off time is 1.12 microseconds about, well, let me get, yeah, right around 1 microsecond, just over 1.1. And if I come over here to get the full time of the pulse, I mean the cycle here, it's 2.2, so yeah, 50%. And up here you can see that we're in the middle of that waveform, so that's right around 0. Now what I want to do is I want to move it to the peak. So I'm going to open it up because it moves over a little quicker. Well, let's see if it does. Oh, there we go. We can move real fast. I got it core setting. Okay, so the green's at the top, and you see the blue waveform kind of come up here at the top. All right, so now let's get the cursors over here. Whoops, wrong cursors. Horizontal ones. I want vertical. All right, so let's get this cursor 2 right here. Well, I'll put it right here. Okay, cursor 1. Okay, and let's get this guy right there. So it's probably just less than a millisecond, 940 microseconds that it's off at the top, and the full time is about 2.2. The frequency has stayed the same, but you can see the off time is less and the on time is higher. Okay, now we'll go down to the negative part of the cycle. Now you see the blue waveform down the bottom. Okay, you can already tell that plus is on less time than the minus. I'll get the cursors over here, just take a measurement. Put it right on that edge. Get the other guy. Okay, on that edge. Okay, so 1.26 off. And again, 2.2. So, yeah, from about 940 microseconds to... So from about 940 microseconds to about 1.24 that is changing with this amplitude. If I increase the amplitude, we should see a little bit more change in duty cycle. So there you go. That's pulse width modulation. And you can see the blue waveform. Let's take the zoom off. Okay, so I had to turn the power supply back on so I could get a THD reading. And here, let's zoom over to that. Now, that almost looks too good to be true. But that's what it's showing. Alright guys, I'm changing the harmonic level, how many harmonics it'll look at. Right now it was only set for 2. Let's go for a bunch. Well, there we go, 17. How about that? How about 27? We'll see what the noise is. That'll go out to some very high frequencies. 27 harmonics of 1K. Enter that and exit. Okay, there we go. We've gone up to 0.02. That is pretty darn good, guys. And by the way, I haven't mentioned it, but I'm using an 8 ohm load. Not very much power, so nothing really worry about there. It's only about 2 watts output. Hey guys, so what do you think? That's pretty cool, huh? These Class D amps are pretty neat. Pretty cool technology. Hey, if you liked the video, give it a thumbs up. If you haven't subscribed, do so. And I'm going to put a link to a playlist that I'll put this in down below. And that playlist, I've done other videos on this. I'm not sure. I think I've done 3 or 4 other videos where I've done phase gain. I've done some power measurements with thermal camera. I think I did an intermodulation distortion test too, where you apply 2 signals and see how they bounce against each other. Gosh, so I'll put the playlist below. I want to thank the patrons for all the support. And by the way, if you guys have some ideas, I think I can do one more video. I got to send this back to EPC, Efficient Power Conversion. It's really nice they let me borrow this, and I've done a few videos and some time went by, so I need to send it back. But let me know. I think I can do one more video on it, and so let me know what you'd like to see. What I'm thinking I could do is show how the signal is processed from input to this power stage. Is that a good idea? Let me know. Okay? Alright, thanks for watching, guys, and thanks for all the support. We'll see you next time.